Today, as you can guess from the screen that I have up here, we're going to be doing a review for the exam next time. So see if you had any things you've been looking at already that you want to cover today, or any homework problems, anything similar to the review problems on the practice set. Otherwise, I'm going to just pick a bunch of these and go through them. Oh, this is not working right. Well, let's look at the first one. I think there's two main topics here, and one of them is solving oblique triangles, and the other one is doing polar coordinates. And so it's not a whole lot of sections. And so let's try just 1A here. Suppose I said solve the triangle. One thing you're going to get is I'll give you three measures within an oblique triangle, a non-right triangle, and ask you to find the other three by saying solve the triangle. Right? There's three angles and three sides, so I give you three and you find three. Solve this triangle with alpha equals 40 degrees. We get a problem just like this. It might be different sides and angles, right? B equals 20 and gamma equals 45 degrees. And the idea is in every oblique triangle that I give you, A goes opposite alpha, B opposite beta, and C opposite gamma. So let's see if I can draw this. I recommend the first thing you do is try and sketch it roughly to the right measure, so you don't fool yourself. So that's sort of 40 degrees, almost 45 degrees. It's maybe a little short, but it's pretty close. And then that could be alpha. And then gamma can come over here at 45 degrees, a little more. And so if that's gamma and that's alpha, then B, where does B go? Well, beta has to go here. So B must go on this side. This is B equals 20. So I have that much out of the triangle. Then opposite gamma goes C, opposite alpha goes A. And I have to find evidently A, beta, and C, right? Stop me at any time you have questions, want to look at this more. But you then have to look at the triangle. Here's one of the big advantages of the sketches. You can see what kind of data you're given, right? What we said was if you're given side, 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 or side, angle, side, this is one way to remember it. Use your own way as you prefer, right? If you're given those, then you go to the law of cosines, right? Because the law of cosines with this information you can write in an equation that has all but one measurement known and solve for that easily. If you try with the law of sines, it won't work very well. There'll be two unknowns in the equation, and you'll go, uh-oh, and second law of sines will give you another two unknowns, and in between them, you can solve two equations and two unknowns. That's a mess. It's easier to drop a perpendicular. So these two cases go to the law of cosines, and in all the other cases, go to the law of sines. If you're given side, side, angle, or angle, angle, side, or angle, side, angle. And then angle, angle, angle is not a congruence theorem. I won't give you that one, right? So there's the law of cosines if I have that. But what do I have here? I have angle followed by side followed by angle. That's not one of those. So we'll do the otherwise. Go to the law of sines, because the law of sines will give you an equation with all but one quantity known that you can then solve for. But every triangle to solve will be one of these two rules. Don't use the Pythagorean theorem. That only applies to right triangles, right? The law of cosines was a generalization of that. Use the law of cosines instead of the Pythagorean theorem. So now, I'm going to use the law of sines for this one then. And what I want to do is write it so that all but one quantity is known, but I immediately run into a problem. Wait a minute, I can't do that with the law of sines. I need gamma with C. One of them is unknown. Then I can use A with alpha. One of those is unknown. I have two unknowns. How am I going to do this? What you always need in the law of sines is an angle and an opposite side. And I don't have that. So what am I going to do? This is the law of sine case, I should say. first, whenever you're given two angles, first thing you do is find the last one. So it's a law of sines case, but first I'm going to find the last angle, then I'll have a nice law of sines case. So beta is 180 minus the other two, so that the three add up to 180, right? Well, this leaves 85 degrees for the last angle. It looks like I didn't draw it quite right. I drew it a little more than 90, right? So, but it's probably close enough. These don't have to be real accurate, all right? So now I have all three angles. I need the two last sides, A and C, and now I have enough to do it because once I have an angle on an opposite side, I can write all but one quantity known. So we'll say the law of sines. So here's sum of angles theorem. Two, the second measurement I can get with the law of sines. Yeah.
Isn't beta 95?
Did I miss it? Subtract. Yeah, sorry, 95. Thank you. Now it looks more like it. All right, so not too far. See, that should be the one reason you draw this is to catch blunders like that. I was just testing you. Very good. All right, so now let's take the sine of 95 degrees. There we go. Is to B, right? Sine of beta is its opposite side B, 20. As a sine of, you can use either one, it doesn't matter. Sine alpha, 40 degrees, is to A. Law of sines applies to any triangle. Now I have all but one number known, right? By taking the angle in its opposite side and then another known angle in its opposite side unknown. So you can solve this however you want. You can algebra cross multiply, or you can take reciprocals of each side. Any preference on this? There's other ways too, actually. Well, let's just take reciprocals, and we'll say 20 is to sine 95 degrees. Reciprocal of the left is the reciprocal of the right, and A is to sine 40 degrees. So that's equivalently. And one thing about this is you don't have to start here. Our law of sines, where you say sine of the angle is the opposite side, and sine of the angle is the opposite side. You can start this way, put side to sine of the angle, side to sine of the angle. Lots of books write the law of sines that way. So if you want, just omit this step and start here, right? That would have been a good idea in this case. Now we'll just multiply by sine 40 degrees on both sides and get 20 sine 40 degrees over sine 95 degrees equals A. Now it looks like I put down my calculator. Let me go get it real quick.
You ready for this test? You ready for this test?
Partially, I need to go over the polar.
Oh, yeah. Polar coordinates.
Yes. Yeah, otherwise, yeah, I'm pretty good.
I'm fine with this part, but yeah.
All right, and then Murphy's law says your calculator will always be in radians mode at this point, so make sure you change it to degrees mode. Let's see. I'm gonna clear this off. And there we go. Okay. So we'll take 20 times sine 40. Close your parentheses here. We'll take sine of the whole rest of the equation on some of these old calculators that don't have a long bar. Divided by sine 95. And I got 12.90. And on this one, I just said solve the triangle. One thing I might do in addition to these instructions, I might say use correct rounding. If I say use correct rounding, then because these are all carrying two significant digits, right? Presumably 20, 40, and 95. I'll round this to two significant digits. So I'll say this is A is approximately 13 by rounding. It actually comes out 12.9. If I don't say round a certain to significant digits, then I might tell you round it so many decimal places, just as though these are exact numbers, but you have to cut off somewhere. All right, so A, and you don't have to use squiggly equal. So there's one measure. There's another. I have one more to find, right? Let's put it up here. Now I can say, similarly, sine 95 is to 20 degrees. I always, or 20, I always like to go back to the old numbers as much as possible in case I made a mistake on my last number. At least I'll propagate it to the next step. I'll say sine 95 is to 20. Similarly, as sine gamma 45 degrees is to C, and then I can solve for C in exactly the same way I just did. Right? So I'll again take reciprocals and go, oh, I could have started with this upside down, right? 20 over sine 95 degrees equals C over sine 45 degrees. Multiply both sides by 45 degrees and have 20 sine 45 degrees over sine 95 degrees equals C. Evidently, C is equal to about 14. Okay. So now, rounding to significant digits there, I wind up with that. Now what you do is you go fill in these numbers. This is the end of the problem, but I suggest since it's so easy to do it quickly that on each of these problems you check it right away while it's still fresh in your mind. So let's put C equals 14 on here. Let's see, A came out to be 13 and beta came out to be 95. And since you drew it sort of to scale, you see it doesn't look like that's reasonable. Just looking at it, that looks like it could be 95, and these look sort of about the same. So drawing a sketch has that advantage of immediately catching some large mistake. If that's 140 and 13, then I don't know I made a mistake. But now you can do these quick tests, just the sanity check, as I called it before. See if the angles add up to 180 degrees, 95 and 40. If I made my mistake before, I'll catch it maybe, right? 135 plus 45 is 180. Sure enough, the angles sum up. Then the three bears check, right? Is the biggest bear opposite the biggest, have the biggest pole of origin. So is 95 is the biggest angle, is opposite the biggest side 20. The second biggest angle 45 is opposite the second biggest side. See, sometimes you'll get these equal if you didn't round to enough digits, but if you round to enough digits, it'll always follow that rule. Largest angle opposite the largest side, and second opposite second largest, and smallest angle opposite the smallest side. Right? And then you just double check if the sum of the two shorter sides is less than the last side, that's a mistake too, right? So those, but I can do that in 10 seconds or something if I have my wits about me at least. And so that one looks all right, at least by the, is the wind blowing in the right direction check. And so now I can, it's not a bad idea when you're all done to come back and check these. I often have students score better than I do because I don't tend to check my answers when I do my run through it. If they check their answers, they might get 100%, I might not. So, check your answers when you're done, but I recommend at this point finishing your test and coming back and checking your answers. Any questions on this one? That one looked all right. So they're solving a triangle in the angle side angle case. Right? Let me do another solving the triangle because there's a variety of these. Let's do 2B here. 2B says this. Suppose A equals 20, alpha equals 40 degrees. And I'll give you these solve the triangle things in degrees. B equals 25, because that's usually what you're solving is for these kind of problems. And how do I solve this one? Same kind of thing, except it's going to come out a little different. So I'll say A equals 20, B equals 25, not degrees, it's a side. So here's B 25. And then alpha might be over here is 40 degrees, almost half a right angle. About 25. And now A equals 20. A is the side opposite alpha. So I ought to make this a little shorter than this one. So maybe it looks like this. A equals 20. So there's what I'm given. And now I notice what kind of triangle this is, right? Part of the sketch is you get side followed by angle, rotating around this way. Side, side, angle is not a side, 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 or a side, angle, side. So again, it's the law of sines, just like last problem. But this is a little more difficult problem because remember, side, 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 angle is the ambiguous case, right? In this case, you could have no solution, you could have exactly one solution, or you could have two solutions. And if there's two solutions, I expect you to find them both, right? So there's my triangle, and let's see. Since I don't have two angles, I won't be able to start off by finding the last angle. Instead, what I'll do is I'll try and use the angle on opposite side that I have, and I'll say sine 40 degrees is to 20, as I have to include this other number that I know, sine beta is to 25. This time it behooves me to put the signs on the top and the legs on the bottom, so the one we have in the book is easier for this one, all right, because I want to solve for beta. All right, so sine beta equals that. If I divide by or multiply by 25 and switch sides here, then I'll get sine beta equals 25 sine 40 degrees over 20. All right. And this will be step one here again, solving for one quantity by writing the law of sines in a way that only one number is unknown. And so I have to include all these three numbers and then one that I don't know. And I can do that since I have an angle on opposite side. All right. Now, since this is the ambiguous case, well, there could be two different solutions. And I could call these A, I guess, since I'm already numbering the sides I'm finding 1, 2, 3. A is that beta could be the arc sine of 25 sine 40 degrees over 20, right? If this is really a triangle, this will be one solution, right? Sine beta equals a number between -1 and 1, always has the solution inverse sine, arc sine. So let's see what that comes out to be. And what happens if my calculator says domain error? A mistake in here. That means there's no solution, right? What'll happen sometimes is you'll get a number bigger than 1 or less than -1 here. You don't even have to go to this step. Just say impossible, no triangle. Because sine beta equals the number always has a solution unless this is bigger than 1 or less than 1. If it is bigger than 1 or less than 1, there's no such triangle, right? You can't make sine beta equal 2 or something, right? So let's try this and say, what's the arc sine of that? And maybe we're done. Who knows? Arc sine of 25 times sine 40, and make sure you close that parenthesis there so you don't take the sine of the whole bottom and then think there's no solution. Divided by 20. And let's see, we get 53.46. So sure enough, there is a solution to this. 53. On this one, instead of using correct rounding, last time I always rounded to 2 digits because I started with 2 digits. This time I'm going to say, suppose I said round to, I don't think I gave any instructions, round to 2 decimal places. That means 2 digits after the decimal point, and I will get this number. Right. So there's beta, and since it's an angle, it's degrees. All right. Now, once I have 2 angles, I immediately do the easy thing and subtract to get the last one. I have alpha and beta, so I say gamma is 180 less the 2 that I have, 53.46 degrees, 40 degrees. So I'll subtract this from 180. Let's see, I got 86.5.
4.
So now I have all three angles. And I just have to find one more thing, that's the last side. With this, I'm gonna need the law of sines, right? So this is a law of sines case, and I've got one law of sines here. So now I'll say finally that, what do I need to find left? I need to find C. So I'll say sine gamma, which is 86.54 I just found, is the C. And then I'll go back to the original problem. I don't care which side you use, but if I go back to the original problem, I'm less likely to put bad numbers in there. Right? Plus, these have been rounded the second time, where those were just rounded, if they're rounded numbers, rounded once to put them in there. So I have sine 40 degrees alpha is to A 20. And now I can solve for C. Right? Once again, you can cross multiply or take reciprocals. All right. So C is the sine 86.54. Minus 20 is the sine 40. Multiply by sine 86.54 and get C equals 20 sine 86.54 over sine 40. Now let's see what that comes out to be. 20 times sine 86.4 closed divided by sine 40. And I get 31.06. Okay, so there's the last side. Now I have the triangle completely solved for, but I'm not finished. Why not? This is a mistake a lot of students make. They get this problem, they solve the triangle, I'm done. Why am I not finished? On side angle, there could be 0, 1, or 2 solutions, right? So I have to check all of them. If there's no solution, then I'll get an error trying to calculate the arc sine. But there could be 1 or 2 solutions still. So that was case A. Now I want to go to case B. What is case B? Beta equals, if there's another case, it's always 180 minus the arc sine. Remember, this is from the picture. There's the unit circle. At this point, I have sine beta equals some number here, right? Suppose it's this one. Sine beta. Well, sine of beta is the y coordinate of the unit circle, right? So if I put the y coordinate equals 25 sine 40 degrees over 20, maybe that's the value sine is supposed to take on. Then there's 2 solutions, this one, and this angle here will be the arc sine of all this stuff. What's the other one? You need to know this for the test.
180 minus x.
There you go, yeah. This by symmetry will be the arc sine of the same. And the angle we want right here will be exactly 180 minus the arc sine. Yeah. So whatever we got here, we just take 180 minus that. And that is our other possibility. 180 minus 53.46 degrees. I should run that on the calculator, huh? Should be 126.54. So there it is. There's the first angle of the last triangle. Now what I'll do is once I've got beta, I've got 2 angles, and I'll look for gamma. Gamma now has to be 180 less the one I just found, 126.54, less the angle that's up there, 40. And what do I get? 180 minus, I guess put second hands to get the last number I had on the display, minus 40. I didn't do that right. Oh, that's because I had the other angle. I'm sorry. Okay, 180 minus 126.54 minus 40. And I get 13.46. Is that a possible triangle? It is. If you get a positive angle here, you're okay. In the case that there's exactly one solution, what will happen is these angles will sum up to more than 100, the angles you have will sum up to more than 180 degrees, and you'll get a negative angle here. So if you get a negative, then you say, oh, there was only one solution. But if this comes out to be positive, then 180 minus the arc sine actually is a solution, and you have a second triangle. So this is the ambiguous case, they call it, where you don't know which triangle it is. So now that I have those, I have to do one last law of sines. Let's say I give you this, I'll take half your test, and it'll be a good workout, won't it? But these do take a long time, unfortunately. So we'll go back again to the original numbers when we can. So, I guess steps again, 1, 2, and 3. Here's the third case, third part of the triangle, the last measure. We'll say sine alpha, 40 degrees, is to A, 20, the numbers I'm given, equals sine gamma, 13.46 degrees, is to C, that I still need to find. And now, again, once you get used to this, you can start to do the algebra in your mind. Suppose I multiply by C on both sides and multiply by the reciprocal of this one. I'll say by algebra, it's 20 sine 13.46 degrees over sine 40 degrees. So you do these enough, you start to be able to do 2 steps in one. I did it all in 2 steps here. But you take reciprocals again and then multiply by sine 13.46. You get that. And let's see what we got. 20 times sine 13.46 closed, divided by sine 40 gives us 7.42. It's 2/4, excuse me. There it is, it's all solved. And now, once again, when you're done, go ahead and check it. This triangle here seems to be the one I drew. 40 degrees. Now let's see what I find. 53.46 for beta. That's over here. That looks a little large, doesn't it? That's the other case, isn't it? That's the one I drew. 126.54. So you want to draw the right one in here. This looks like it's bigger than 90. So that's the advantage of drawing this accurately. 126.54. And then 13.46 for gamma. That's over here. So that looks a lot bigger than 13.46, but it may be my drawing's kind of poor in this case. And then C has to be 7.24. All right, so there's one possibility, and you just go through and check it and say, do the angle sum up to, oops. Oh, yeah, it looks like 113, but it's 13. Do those angles sum up correctly? 166, 176, yeah, it looks like it sums up to 180. Largest side, largest angle, second largest, second. Okay, that's good. And then the sum of the two sides, 27 is more than 25. So it's all the basic checks check out. That's probably right. That was the second one. That was the one I was most worried about. Now I'll go figure the other one. If I keep these original 3 measures, there is actually another triangle I can get, and that's this one. Let's see, in that one, angle beta is a lot smaller, so this one beta would be 53.46, opposite B, and then gamma would have to be 86.54. That would be opposite C here, so this would be 86.54 degrees. And C would be 31.06. And does that work out? Once again, if I sum the 3 angles, let's see, 93.46, 73, 179, yeah, it looks like it adds up to 180. The largest angle opposite the largest side, sure enough. And the second largest, let's see, would be this one, opposite second largest, yeah. It is 20 on this side. And then 2 sides, let's see. 31.06 is bigger than 20, is smaller than 20 plus 25, so it does all the checks, that's probably right. So there's the two triangles, for 2B. That look all right then? Make sure you can solve triangles, that's more than half the test probably, right? Well, let's do at least one more triangle case, because I haven't gotten to the law of cosines yet, right? Now the law of cosines. Let's try this one, the very last one, 2C, 18, 15, and 10. So suppose B is 18, B is 15, and A is 10. We're given what kind of data? We draw this picture. 15, a little longer, 18, and 10. And since we look at it at side, 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 that's the law of cosines case, right? If you forget this rule, you can kind of see it. Whenever you're given an angle opposite side, you're going to wind up wanting to use the law of sines. That's another way to think of it. You can't figure an angle on opposite side when you figure out what angles, and you got to go to the law of cosines. All right, so I've got law of cosines because it's side, 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 or side angle side. With the law of cosines, it doesn't matter. With three sides, it doesn't matter which angle you find first. You can still solve it, but there is a strategy that makes it a little easier. So I recommend starting with the largest side in the side, side, side case. Start with largest side, and this has a good reason for it. If I start with the largest side, I'm going to find the largest angle first, right? With the law of cosines. That's good because the law of cosines has no ambiguous case, right? I won't have to say, well, is it gamma or is it 180 minus gamma, right? Law of cosines, there's no ambiguity. And then on the other angles, I'll know that the other angles are acute. When I use the law of sines for the next one, I won't have an ambiguous case because I've already found the largest angle. So let's say if you find the largest angle first in the law of cosines, that could save you an ambiguous step at the next one. But it still works either way, so I'll take the answer. Start with the largest side. I'll start with C and say C squared, 18 squared. Well, let's write it down. Law of cosines is this: C squared equals A squared plus B squared what? That looks like the Pythagorean theorem, right? Minus 2AB cosine gamma, because it's law of cosines. This one was always hard for me to remember, but if I remember, it's Pythagorean theorem: C squared equals A squared plus B squared minus 2AB cosine C, right? This is thinking big angle C in the other notation. So if you know your ABCs and Pythagorean theorem, maybe you remember it. A squared plus B squared minus 2AB cosine gamma. And now in the side, side, side case, I have all but gamma known here. So I'm going to get 18 squared equals 10 squared plus 15 squared less 2 times 10 times 15 times cosine gamma. I know everything but gamma, so I'll just solve for it. I'll subtract here and get 18 squared. So these are all equivalent statements. Same solution set. Minus 10 squared minus 15 squared equals, let's see, this is 150 times 2 is minus 300 cosine gamma. And so now I divide by negative 300 and get cosine gamma equals 18 squared, 10 squared minus 15 squared, all over negative 300. That's going to give me a negative number. Is that right? If it does, that's okay, actually. The cosine can be negative if the angle is obtuse. We'll see if it gives us a negative number. Maybe it won't. So 18 squared minus 100 minus 225, if you have those all memorized. I'll compute the top, and in fact, it is -1. So this is negative on top, but it's negative on the bottom. It's going to cancel it. And I get, let's see, cosine gamma. Now gamma is equal to the inverse cosine of this number, 18 squared minus 10 squared, 15 squared, all over minus 300. And so we'll take inverse cosine of that and get 89.8. We got almost a right triangle here, 89.8 if I round it to 1 decimal place, degrees. So if I drew this correctly, I guess I didn't quite. This would have to be almost a right angle, so it looks like that. There we go. So hopefully that's right now. This is now 89.8. And now, once I've got the law of cosines for the one case, I can use the law of cosines again if I want, but most people use the law of sines because it's easier. And if you found the largest angle here, that guarantees the other two angles are acute. You don't have any ambiguity. You just take the inverse sine. So let's try the law of sines for the second step. And that's what people like to do here is we want to start with the largest side law of cosines. In the side, at least. Then go to the law of sines on the second step, because now you have an angle on opposite sides. So I'll say sine gamma at 89.8 degrees equals to C, 18, as, so let's say sine alpha is to A, 10. And I can solve for alpha. So now let's multiply by 10, and I get 10 sine 89.8 degrees over 18 equals sine alpha. And I write immediately, alpha is the arc sine. There's not a case of 180 minus because this has to be an acute angle, so it can't be a 180 minus. Alpha is automatically the arc sine, sine 89.8 degrees. Must be acute. Acute meaning less than 90 degrees. And we got inverse sine, sine 0.8 closed divided by 18. Again, the triangle doesn't look like that. So what do we do? Oh, I forgot my 10. That's what I did. See, that's how you catch it. You look at the triangle and you catch it. Okay, let's try again. Arc sine 10. Sine 89.8. Divided by 18. Now I get 33.7. Like squiggly, because if you want, indicate your rounding. And now, once again, once you have two angles, don't mess around with lots of numbers unless you make a mistake. Just go to the sum of angles theorem and say the last angle, alpha, a beta, excuse me, must be 180 minus 1.5. 180 minus 33.7 minus 89.8. We've got 56.5. Okay. There's a law of cosines problem. Start by finding the largest angle, then you won't have an ambiguous case of the next step, but it still works if you don't do that. Look, all right. That's solving triangles. That's a large part of the exam, being able to use the law of sines or the law of cosines, figure out which one to use, figure out if it's the difficult 0, 1, or 2 solutions case. There is one more interesting case I'll put up here that I could put on the exam. Not everything in the exam is necessarily going to come off of this practice sheet. What if I said this one, solve the triangle, and this time I'll give you side data again, with A equals 4, B equals 6, and C equals 12. What do you say with that one?
Not solution.
Yeah, immediately on this one, you might get this kind of case. No solution. You can do the check before you start. When you're given side data, the two shorter sides have to add up to more than the last side or there's no triangle, right? No solution since some of the shorter sides is less than the longer side. If you try and solve this, you'll wind up finding something's wrong as you go and you'll wonder where you made a mistake, but the mistake was, this isn't really a triangle, right? And once again, I'll draw it again. If this is 4 and 6, and this is 12, then the shortest distance between 2 points is not a straight line. It's going around here. That's impossible. Okay, so be aware of that also. Now, there are applied problems I want you to be able to do also. I expect to put at least one word problem on here, so that's the next thing coming up here. Have any preference on which of the word problems I do here, 5 or 3 or 4? There were some other word problems on the homework that might come up also. Don't just do these, but make sure you do these. These are very likely one of them to be on there. Number 3 then. 2 observers stand on the ground, it says. Directly south of a hot air balloon that's passing by. One observer, so sketch this always for word problems, make a sketch. That not only helps you catch mistakes, but it also helps you to have insights into things that weren't directly given. You can get, suppose the hot air balloon is over here. 2 observers are back here somewhere. And they're directly south, so this is the direction south along the ground, but this is a side view. Now, one observer measures at 30 degrees and the other one 25, right? So the one that's further away has to be the 25 degrees. We'll assume level ground unless the problem says otherwise, in which case that's a right angle. So this is 25 degrees. And then from the measured angle up from this observer will be 30 degrees, it says. And now if the ground is, let's see, the other observer is situated half a mile further south. So this is 0.5 miles here. And again, angle of inclination is the angle up from horizontal, like a guy for it. The ground is level. What must be the height of the balloons? We're finding height 8. So what you do is you put in all numbers you know. We're given these 3 and the one you're trying to find. And now you say, how can I solve this triangle? Here's where the sketch is beautiful, because if I'm just trying to find that from the numbers, I don't actually have enough numbers to do it, right? And this little triangle here, I only have 2 pieces of information. I need 3, right? In the last problems, I give you 3 and you find 3. So I can't solve that one. In this big triangle here, well, I only have this angle and I don't have anything else, so I can't solve that one. And in this one, I have this angle. There's not enough information to solve any of the 3 triangles that are there. All right. So what do?
Supplementary.
There you go. Yeah, you use the picture to deduce some new things. I notice in here exactly, these are supplementary angles that make a straight angle between them. So this one must be 180 minus 30. It must be 150 degrees. So I'll get that as a secondary case. Now I have it, angle, side, angle, right? So I can solve that. It's not side, or side angle side. It must be the law of sines to solve this one, right? The law of sines case. since I have two angles, I might first find the last angle. But actually, I don't need to solve the whole triangle. All I'm looking for is h. And so you think ahead, how do I find h? I need to find something else in this triangle besides the angle, right? A right triangle, I just need two pieces of information other than angle. I can get this angle in any other side at all. I can solve this thing, right, as a right triangle case. So what if I can find this one, because that's also in this big triangle. I want to find this one, but alas, I don't have the information to solve it. Maybe I do. Let's see. Side and an opposite angle, but I don't have another side and opposite angle. I am going to have to find this angle first. So I'm going to start by finding this angle up here, just so I can get to this side here that I need. And we'll say, what is that angle? Oh, it's easy. This one now is 180. Take away, in fact, it's not a bad idea to just go through and from the sketch deduce everything you can quickly. Once you have these two, I say, oh, the sum of the angles in a triangle is 180. So this one is 180 minus 25 minus 150. It's a tiny angle of 5 degrees. That's a 5-degree angle up there. Now, some of these numbers are exact. Otherwise, I'll be rounding one decimal place everywhere. You can probably guess the answer. Once I have this, now I can use the law of sines, right? So this picture is beautiful. It helped us a lot. I can use this angle on this opposite side, sine 5 degrees, right, 30, 55, I'm sorry, 150, 170, yeah. Sine 5 degrees is, this angle is to the opposite side, 0.5 miles. As, well, I'm trying to find this guy here, we could call this C, just to give it a letter, as sine 25 degrees is to C. There we go. Once again, it would have been better to write the law of sines upside down, but this will work. A little algebra, I multiply both sides by C, and I multiply both sides by the reciprocal of this one. I'll find out by algebra that C is 0.5 sine 25 degrees over sine 5 degrees. I'm doing that faster now. It's equivalent to taking reciprocals and then multiplying by sine 25. All right, so now by algebra, I have that, and multiply that out. Let's see, 0.5 times sine 25 close divided by sine 5 close. And I get about 2.42 roughly. Did I say how many to round this to? I forgot. Rounded 1 decimal place. So I've got to carry at least 1 decimal place here. Here's C. All right, that's that one, and it's in miles because the other side I used was in miles. And now what I'm trying to get to is h. Now I have this side and this angle in a right triangle when I solve this one. So I say, finally, what is the right triangle relation that relates h and c and 30 degrees, right? So let's see, the sine of 30 is h over c, right? So now I'll write sine of 30 degrees is h, the opposite side, divided by c, the hypotenuse, 2.42. And by right triangle trigonometry, I multiply both sides by 2.42 and deduce that h is 2.42 sine 30 degrees. Now, you can, if you want, run this in your calculator, but once in a while you're lucky and get a special angle. I remember maybe the sine of 30 degrees is a half, right? I have this triangle here, 30 degrees, 1/2 square root of 3 over 2 and 1. So all I have to do is multiply this by a half, and oh, it's 1.21 miles. Use the calculator, or if you recognize a special angle, sometimes use that. How about that? Now you can go back and check this thing and see if it looks all right. But since we didn't solve the whole thing, it's mostly just looking at the picture and seeing if it sort of makes sense. Is it really likely this is 1.21 and this is 0.5? Yeah, it could be, right? And so This is 1/2 of this one for a 30-degree angle, so that's correct. So it looks like it's probably right. But again, when you're all finished with the test, go back and look at it. Questions on that one? Okay, good. Let's look at some other ones then. The rest of the test is polar coordinates then, right? Those are all the triangle problems that we have. We have law of sines, we have law of cosines, we have word problems. Among them, you want to be able to do the ambiguous case for the law of sines, and you want to remember that trick to find the largest angle first when you're using the law of cosines. Let's try polar coordinates now. Let's do number 7 here actually first, just for fun. It's kind of an easy one. We need a break from all those long-winded word problems, right? Let's see, I'm gonna put this screen on here. And this is amazing. People always think they know this one because it looks so easy. But it's always a mistake. So what if I want to find the points that have these polar coordinates? The first one is r and the second one is theta always. Whether or not I put a pi in this, right? Pi can be any real number, any decimal number. I don't have to use a pi in here. But suppose I said it's r equals 2, theta equals pi over 4, plot that. Well, 3 pi over 4 isn't marked on here, right? Every 30 degrees is marked, every pi over 6 radians. So how do I find 3 pi over 4? Well, you just remember, right? Here's pi over 2, here's pi. 3 pi over 4 is halfway through here. So I would mark it halfway through here, and then I just go out 2 units of 2 circles, right? 1, 2. So right there will be this 4th point. That's the easy one when they're both positive. The trick is when you get 1 or 2 negatives. How about this one? -4, 5 pi over 3. Well, I'm lucky 5 pi over 3 is marked, so I go all the way around and turn to the angle and then go out the distance is what you do. So I'll turn to 5 pi over 3, but since it says -4, instead of going in the direction of 5 pi over 3, I back up 4 units. 1, 2, 3, 4. So I plot that point right here. Here's part B, is this point in the direction of 2 pi over 3 because you back up 4 units, right? And then here's this one, 4 pi, right? This one, I'll turn to the angle pi, turn to the angle first, and then go up 1, 2, 3, 4. These are pretty easy problems. I might ask you something actually harder on the test. What if I said 17 pi over 6 for the angle? Sorry, -17 pi over 6, and -3 for r. So let's try this one. -3. -17 pi over 6. I gotta put some harder ones on there just to make sure you plot these. All right, let me put this back so that you can see it online here. All right. Find the point r equals -3, theta equals -17 pi over 6. How about that?
Add 2 pi.
Yeah, you could add 2 pi to that and get the same direction. So that'd be add 12 pi. That's the same as the direction -3 -5 pi over 6. Now I can do it. Let's see. -5 pi over 6 means I go clockwise 5 pi over 6. That gets me to 7 pi over 6, right? You could add 2 pi and say it's the same as 7 pi over 6 is another. So I'll go -5 pi over 6 like that. And now I'm in this direction for theta, but I want to go -3 units, so I back up 3. 1, 2, 3, right? So see, some of these are tricky, right? Especially if I put it down between the axes at one of those. Maybe I don't want to be that dastardly, right? Anyway, there's how you plot that one. So I want you to be able to plot any points that are in the polar graph paper. This is just like rectangular graph paper. You have lines of constant x, right? Vertical lines, x equals 1, x equals 2, x equals 3. And horizontal lines, y equals 1, y equals 2, y equals 3. Similar here, it's r equals 1, r equals 2. Here's all the points in the plane where r is equal to 2. Here's all points where r equals 3. And then here's all the points where r is positive, and theta equals pi over 6, and theta equals pi over 3, and pi over 2. So it's just like graph paper. You plot these curves of constant values of the coordinates r and theta, and then you get this radar-like image. All right, let's look at some more interesting ones then. Again, the answers are at the back, so you can check your answers. Suppose I say convert one of these things. Any particular problem I'm going to look at? 5A. Okay. So 5A says this, convert the rectangular coordinates -3 to polar coordinates. What you have here is, this is the hard direction, is two equations. You put down r squared equals x squared plus y squared. What I might do is like the homework too, and say, instead of saying such a simple thing as find coordinates, I might say find one coordinates with r positive and one with r negative. So I'm going to do that here in case I'm in a bad mood when I make the test. R, but I might, no, I seriously might do that. R squared equals x squared plus y squared, and tangent theta equals y over x are the two conversion equations to get rectangular coordinates to polar coordinates, right? It's all rectangular here, gives you the polar on the left, but it's not a direct conversion, right? What I first find is that r squared equals -3 squared plus -3 squared equals 9 plus 9 is 18. Well, if 9 is 18, I have r squared is 18. I have two choices for r. R could be the square root of 18 or minus the square root of 18. I can choose either one, right? You can choose r positive or negative. They both work. Let's be easy on ourselves since we're taking a test. We'll let r be the positive square root. Don't leave it like that as a point off and answer. See why. You didn't simplify. This is a correct answer, but it's right. Square root of 2 times 9. You want to write square root of 9 as 3. So this will be 3 square root of 2 is the proper answer for that one. There's r. This is if you choose r positive. You can also choose it to be negative. Once you've chosen r positive, that means you want theta to go into the same quadrant. So we want tangent theta equal y over x -3 over -3 is 1, right? And you ask yourself then to put it into the same quadrant as this one, which was over here, -3, it's in quadrant 3, right? So if I choose r positive, I want to put theta in the same quadrant as the original point, quadrant 3. So I ask, what angle has tangent equal to 1 in quadrant 3, right? We know how to solve that. Remember solving the last test? Trig function equals a number. That's what this is. I'm solving, getting near the end of the period. I'm solving tangent equals 1 within quadrant 3. So I'm going to be over here, and I can draw the unit circle. How do I solve tangent equals 1 in here? What we said is you could rewrite this as tangent theta equals the quotient 1 over 1, and then divide both of these by the root sum square of these. Square root 1 squared plus 1 squared. Oh, it's square root 2. And so this is 1 over square root 2 over 1 over square root 2. And I recognize those as being from a 45, 45, 90 triangle, right? 1 over square root 2 or 2 square root 2 over 2 is the same number, right? That's a 45, 45 triangle. So this angle here must be 45 degrees. Probably I'll ask you for radians on these polar coordinate things. So I'll say that's pi over 4. Well, if that's pi over 4, then the angle I want, get all the way around here, this one is, let's see, pi plus pi over 4. Great angle plus 2. Well, this is 4 pi over 4, right? Plus pi over 4. Converting them to a common denominator. Then add the numerators. 4 pi and 1 pi is 5 pi all over 4. There's a good angle. So theta equals 5 pi over 4. And now I have one set of polar coordinates are 3 square root 2 and 5 pi over 4. There's polar coordinates for that point. And you can kind of figure it in your mind since you just did the graphs, right? Turn to 5 pi over 4 and go out 3 square root 2 units. Just do it up here. 5 pi over 4, that looks about right. Does this look like about 3 square root 2 away? Yeah, if it's 3 by 3, this is 3 square root 2, right? Because it's isosceles right triangle. So you can kind of check it like there's polar coordinates. Now suppose this is with r positive. What if I want ask you also to find polar coordinates with r negative, right? Maybe I'll ask that. How do I do that? Once you find the positive ones, the negative ones are easy, right? What you now want is just take minus whatever r you got here, so it's minus 3 square root 2. And what do I do with the angle? You add or subtract pi to make it the opposite direction. You want theta to go into the opposite quadrant. So if you make r negative, then you just take minus this r, and then you put theta into the opposite quadrant. I can either add pi or subtract pi. I think it's easier to subtract pi. And I'll say that with r negative polar coordinates are minus 3 square root 2 pi over 4. And you gotta kind of check it on your polar graph papers. If I go at an angle of pi over 4 here, and I back up 3 square root 2, sure enough, I get to the same point. And then you can add 2k pi to either of these, and they're also allowed polar coordinates. So I have to check your infinite number of possible answers, right? So, but those are easy angles, polar coordinates. This one with r positive, this one with r negative. So be able to do that. Now let's see. We want to convert some equations is another one. Let's look at 5a and say convert to polar coordinates. The equation 2x squared plus 2y squared equals 8x. First thing I might want to do with this is divide through by 2, since all these numbers are divisible by 2, and I'll write equivalently just to save myself some work. X squared plus y squared equals 4x. That'll be easier. Now, what can I do? With the idea in these problems is you have 4 conversion equations. I wrote 2 of them over here. R squared equals x squared plus y squared. Tangent theta equals y over x. X equals r cosine theta, and y equals r sine theta. You want to use one of those directly. When you're converting from rectangular, you can always just plug in x equals r cosine theta and y equals r sine theta, and it does work every time. However, the point of this problem is to say sometimes it's easier just to use all of these equations. So rather than plugging in r cosine theta squared, r sine theta squared, and r cosine theta, which works, it's a lot of simplification. It's easier to say, wait a minute, I've got x squared plus y squared. I'll just replace this with r squared by that first equation. Right? And then 4x is 4, and now substitute for x r cosine. So there is a polar coordinates equation for this. I can do a little better than that if I think about it. What's a better equation than that? Simplify it. A factor of r on both sides, I can divide both sides by r and say, finally, this is r equals 4 cosine theta. This is the best polar equation for this circle. Given away, it's actually a circle, not at the origin, but there's a good equation. All right. You have to be careful when you divide by r, you assume r isn't 0. But r equals 0, the pole is a solution here. It still is here when you put theta equals pi over 2 and r can be 0. So I actually didn't lose the pole by dividing by r. So there's a good equation for that one. You want to simplify it as much as possible. But it is really easy going rectangular to polar in the sense that you can always just put in, replace x with r cosine theta and y equals r sine theta and do a lot of simplifying. But use this step and save yourself some trouble there when you can. Let's see. The harder part is doing these other ones on problem 8 when you want to convert the equations from polar to rectangular and sketch. So convert to rectangular. This time I said Cartesian. It's the same thing. Convert to rectangular, or also known as Cartesian after Descartes with the coordinates, and sketch it. Here's the graph, A, R equals 3. What's that? This one you really want to have memorized. What is that immediately? R equals 3 is the set of all points at a distance 3 from the origin, right? R is a polar radius when it's positive. And so this is just the circle of radius 3. I can draw it as quick as that. R equals 3. However, if I want to write it rectangular coordinates, what do I write? You can write the equation for a circle is good. Here's what I like to do just to complete the problem. R equals 3, how do you convert that to rectangular using just these equations? You don't want to put R equals square root or minus square root of x squared plus y squared. Instead, square both sides, write R squared equals 9. By squaring both sides, now you can substitute directly because you're substituting for R squared. So we'll say this is x squared plus y squared equals 9. There it is. Obviously a circle, right? X squared plus y squared equals R squared is always a circle at the origin. This is the standard form of the equation. Remember the standard form of the equation for a circle? You put x minus x naught squared plus y minus y naught squared equals R squared. Is the circle of radius R centered at x naught y naught. So this is a circle centered at 0, 0 with radius 3 is what that is. And so you can sketch it from that too. But you can sketch it either knowing that R is the distance from the origin when it's positive, or by converting it and then drawing it, either way. So that's an easy one, but I want you to recognize a circle. Suppose I said you instead sketch R equal minus 3, what would you do? Uh-oh, negative. When R is negative, it's the distance from the absolute value is the distance from the origin. You're just backing up on the angle. This is again all points at a distance 3 from the origin where you just back up 3. It's the same circle intuitively. And indeed, if you square both sides, you get the same equation, you get the same circle. So this is also, if I give you R equals minus 3, it's also the circle of radius 3 and has this equation. It's the same thing. You just square both sides and get this. All right, so that's just a side note. Maybe I should have made it tougher of a practice test time and give you the easier ones in the actual test. How about theta equals 3 pi over 4? I want you to recognize if you have theta equals a constant number, what does that sketch out to be?
Straight line.
Yeah, it's a straight line because now I'm turning to the angle 3 pi over 4. Saying I'm going to go with this fixed angle, but R could be anything. So like R can be 0. I get the pole. It can be a little bigger, a little bigger. R can be any number. I can move any distance out I want. And R can be negative, and then I move in the opposite direction any distance I want. So it's this straight line right here. There it is. Theta equals 3 pi over 4 is that straight line. If I want to find an equation for it, though, I do. I want to use one of these conversion equations, right? I could take cosine theta multiplied by R, but then I have an R over here. The easy thing to do is take tangent of both sides. Tangent theta is tangent 3 pi over 4. Right? Tangent theta can be replaced by y over x. So I've got y over x equals this number, tangent 3 pi over 4. X, I can do tangent 3 pi over 4, right? It's a special angle. This one. What's the tangent of that angle? Well, this is a pi over 4, right? So this, the tangent is this side over this side, square root 2 over 2 over minus square root 2 over 2. All right, and so the tangent is minus 1 from the unit circle. Well, if y over x equals minus 1, then y equals minus 1 times x. It's that line right there. There's the equation for it. It's just y equals minus x. And it's a line, theta equals a number as always by this argument here. A line through the origin whose slope is tangent 3 pi over 4. That's what we got here. Line through the origin with slope minus 1, the tangent of 3 pi over 4. Then the trickier one, I should have put more of these on here. I will do one extra. Oh, I erased my equations I need. Fortunately, I don't need them for long, right? C, suppose I asked you to sketch R equals 4 cosine theta. I gotta put some more problems on here. There weren't enough on this one. How do I do that one? Using my conversion equations, right? R squared equals x squared plus y squared. Tangent theta equals y over x. memorize these, you need them in your later courses. X equals r cosine theta, y equals r sine theta. Again, the same instructions. Convert to rectangular coordinates and sketch. How can I use these equations to convert that? I don't want to put theta equals arctangent or arctangent plus pi. That's too complicated. Instead, this time, instead of squaring, I'm going to multiply both sides by r. I'll get r squared equals 4r cosine theta. And that's an equivalent equation. I have to be careful. I introduced the polar solution, but it was already a solution, so we're okay. So I'll multiply both sides by r and get that. And now I can convert it because r cosine theta is just x. And r squared is just x squared plus y squared. There is a legitimate equation. However, if I want to sketch it, how am I going to sketch it? This is the trick. I want you to know this because you see this in calculus probably. You subtract the 4x over and complete the square from algebra. So I'll write x squared minus 4x plus y squared equals 0. To make a perfect square out of this, when I have an x squared term and an x term, I have to add half of this number squared, right? So I'll take 1/2 of -4, square it. Well, let's see, it's -2 squared is 4. So I need to add a 4 in here to make a square. Right? And if I add 4 over there, I need to add 4 over here so I don't change the solutions to the equation. But now I've got it right because this is the square x minus, it's always x plus half of this number. This is the square of x minus 2. Y squared just stays the same, and you've got 4 on the right. And what's that an equation of? If you think about it, that's x minus 2 squared plus y minus 0 squared. I'll write it more suggestively here, equals 2 squared is a standard equation for a circle. At 2, 0 of radius 2, right? So this is a circle at the point 2, 0, the numbers that are subtracted. Radius, whatever squared over here. Capital R equals 2. So I can sketch that easily, right? I'll just go on here and go out to 2, 0, 1, 2. And if it's radius 2, it just comes back to the origin here, and it looks like that. Right? There it is. There's the sketch. Right out here, 4, 2, and down to -2. Okay? Well, that's one last problem here, because I might give you this one as a test. All right. What if I said D R equals 2 secant theta? What do I do with that one? Again, I want to get one of these things, right? I think, wait a minute, what if I multiply both sides by cosine? I get r cosine theta equals 2 secant theta cosine theta. But these are reciprocals, they cancel, right? R cosine theta equals 2, r cosine theta is x. This is just the vertical line, x equals 2. So sometimes you just need to multiply through to get, r cosine theta, r sine theta, y over x, or x squared plus y. This one is easy to sketch now. Let's go to 1, 2. It's the vertical line, right? Well, that's quite enough. It looks like the time is up. Hopefully that gets you ready for the test. That's the kind of things I want to ask, be able to do problems, solving triangles and doing polar coordinates, equations and points and plots. Thank you.